Okay, let's talk about week 6 through 9. We've talked about the various things you need to do to get your study started. We looked at your variables, we looked at the hypotheses formation, research questions, and purpose statement. And I started talking about scales, and I want to talk about that in a little bit today. But let's talk about the design of your research now that we're getting a better idea of what we might be looking into in terms of the research study. And in Canvas or Blackboard, excuse me, I posted an announcement for week 6 through 9. These are the things we will be doing for the next 3 weeks. Some of it will be on your own and then one-on-one. I'll be sending you emails. We'll be going back and forth on thoughts and kind of clarifying the direction in which you'll be going for your research study. Now, the main goal is to create what's called a proposal. That's our main goal. Our goal is to complete a research proposal, which is the step before you actually go and collect the data. And the reason we do a proposal is so that you have a clear idea of what you're doing before you actually do it. So that it's kind of a guiding document, a guiding path as to what are the steps I need to do, what are the things I need to be making sure I'm aware that I'm trying to collect, and make sure we're following a strict path of our research design. And so before we can go into the proposal or the elements of the proposal, we need to start talking about what research design we're going to do, whether it's experimental, correlation, ex post facto, or something else. But those three are the main ones that I'm seeing based off the 10 points that you guys have given me. And then deciding what type of analysis you will use for your research, whether it's a t-test, a correlation test, or a regression test. Most likely, most of you will be using a t-test statistical analysis between two groups to measure performance, let's say, between two groups, two pilot groups, or two scenarios, things like that. So those are the main two things we'll be doing this week. I want you to start working on the scale or deciding on the scales you will be using for your study so that we can measure, let's say, between two groups what you're going to be measuring, and then working on your document proposal. I've also outlined what we'll be doing between weeks 9 through the end of the semester. So let's go and find out the content for this next few weeks. If you go to course content, and under here, weeks 6 through 9, I've posted a number of documents that I want you to be reviewing in your own time, but I will be going over at least the quantitative research design, an example proposal, and then data analysis overview. And then once we have an idea of what types of statistical analysis you'll be doing, I'll be going over the t-test and correlation research in more detail. So let's start off with quantitative research design. And so if you click on this, it should pull up the document. And I can discuss the various elements of quantitative research design. So we are trying to do a quantitative research topic or a study because we want to analyze numbers. We want to actually look at numerical data and be able to come up with an inferential analysis as to what is happening, trying to model what is happening in the real world. And so we're trying to look at relationships. We're investigating data and their relationships. It's very systematic. There's correlational research. So correlational research is looking at the relationships between two variables and seeing if they increase or decrease. And I'll go into a little bit more detail about that. But what I wanted to show is, let's see if I can do this over here. Is if we have two variables that we want to measure. We want to say we want to look at performance is the dependent variable of a pilot versus the number of hours the pilot has, right? And it should be kind of intuitive that it should look something along the lines of this, right? This is just a basic example. What this shows us is the greater the number of hours the pilot has, the better the performance. There is a correlational element to those two variables. And that's something we may want to examine and see if this is actually the case. So the hypothesis may be the greater number of hours, the better the performance of the pilot, right? And this is just a basic example. And you can see this line kind of gives us an idea of the relationship, the strength of the relationship, but also the magnitude of the relationship. I can now predict if this correlation is strong, that this number of hours will give me this sort of performance from a pilot. When I collect this data, let's say I have 100 participants with different number of hours, this is what it would look like if I were to plot it out, right? The number of data sets would give me this sort of information, and then I can plot a best line that measures the average relationship between the two variables. That will give me an idea of the strength of the analysis or strength of the relationship. Now, if this line looks different in the sense that it starts looking that way or starts looking this way, these different lines based off the data sets will give me an idea of whether this data is strong, weak, or how much of a difference in magnitude there will be between the two variables. So that's correlational data, all right, a correlational data set. So we want to look at terms of magnitude and terms of increase or decrease. Correlational data really works well for two continuous variables. So performance can be continuous from 0 to 100% in terms of that scale, and number of hours can be from 0 to 100 hours or 200 hours or 1,000 hours. So your scale has to be continuous. Remember, we talked about continuous versus nominal data or categorical data. So if we have categorical data, we can't use correlation, right? If we're looking at male versus female on the x-axis and looking at performance, you're not going to get a correlation. You're just going to get two sets of numbers with respect to the chart that I was examining. So if we looked at it again, let me go back to my graph over here. If I was doing a similar study, performance again, while that is continuous, but then I'm looking at just two different sets of data, male versus female, well, I can't tell a correlation there. I can't say if you're female, you're gonna, there's no real correlational data there. It's basically what is the difference between these two groups, and that relationship does not conform to correlational data. So we have to look at a different type of research analysis, that would be experimental, and a different set of statistical analysis, which would be a t-test, a test between two groups. So back to correlational. Correlational indicates the strength and direction of linear relationship between variables. We want to try and keep it linear at this stage in research studies because we're not quite yet there for non-linear correlations, but let's look at just linear correlations. And what are the significance? So what we're asking is there a relationship between two variables or sets of data? What is the direction? Is it positive? Is it negative? Maybe number of hours will decrease performance. So if you increase your number of hours, you decrease the number of performance or ability of performance. That would be a negative direction. Magnitude could be strength, right? How strong is that? So what we're trying to do is show any tendency of the variables to vary consistently. So how consistent is the variation? We use something called the Pearson's product moment of coefficient from -1 to +1. And so it looks kind of like this. You can either have a positive, strong correlation if it's close to 1. If it's half, that means it's a medium correlation. If it's under half, it's kind of a weak correlation. Maybe the dots are very spread apart, so it's not a very strong line. -1 would be a negative correlation, so as x increases, y decreases, as you can see here. R equals 0 means these dots are all over the place. It's not very strong. I can't really tell if there is a correlation between x and y. It's all over the place. This is a curved line, so this is a curvilinear or curved nonlinear correlation um, relationship. And so that's a different analysis and a different discussion in another class, maybe in a grad school or PhD school. All right, so another type of research design, so there's correlation design and then statistical analysis and correlation, but then another type of design would be ex post facto. What ex post facto means is from what is done afterwards, if we were to translate that directly. What that really means is you're using data that's already out there. So you're using historical data to examine either a correlation or a relationship between two variables or two sets of data. So what an example would be, you're looking at the number of accidents as one variable and looking it up in the NTSB data site, and looking at number of hours, or sorry, let's say number of operations in an area. Let's just hypothetically say that. Both of those data sets per year, let's say, both of those data sets would be historical data from a database like the ntsb.gov website, and that's just you pulling out that data from that website, cleaning it up, and looking at it in terms of either a t-test or correlational test statistically to come up with inferences. So I want you to keep in mind that correlational research or research design is a design on its own, and then there's also correlational statistics. And then ex post facto is a design on its own, and you can use correlational statistics to measure relationships between two variables in an ex post facto point of view. So what these studies are, ex post facto studies, they're looking at possible cause and effect relationships by observing an existing condition and searching back in time for plausible factors, right? Plausible causal factors. Ex post facto research is pretty good for accident research, looking at accidents in the past over time and kind of getting an idea of what's going on and finding out causal reasons, looking at correlations, looking at predicting values, things like that, using statistics to analyze post research, so post data that's already been done. So we can also use that to do different things in terms of market analysis, looking at historical market analysis and predicting the future based off historical analysis, things like that. Characteristics of ex post facto is what you're trying to do is look at dependent and independent variables, or we call them now the effect or dependent variable, not independent and dependent, but effect versus dependent variables, and examine it retrospectively. So we're looking at it from a historical point of view. And what we're doing is establishing causes, relationships, or associations based off that data set by looking at the statistics based off that. You have no control over the variables, so it's already been done. So all you're doing is taking that data set and kind of looking at seeing what's going on with that historical data set. So when should you use that? So ex post facto is really good for when you can't use experimental designs where you're seeing an effect between two sets of data, let's say, or two sets of people, groups, or two sets of variables and trying to manipulate it. Or you can't control factors, or you have data that's already out there that hasn't been looked at in terms of correlations and relationships, and you're trying to find out the best way to examine it. So advantages. So it does allow for correlational research in terms of statistics to see if there's any things that are related to each other or the causal factors. It's exploratory in the sense that you can examine data and see what relationships are to potentially look at future research. It does show cause and effect relationship. Disadvantages you can't control. You're never certain if there's an actual causative factor that's been included or identified. You're just using historical data. And it may be regarded as too flexible. You're not really examining factors from an experimental point of view. And then lastly, experimental is what we do want to try and do. In most cases, it just depends on your design. Some of you will be doing ex post facto. Some of you will be doing mostly, some will do correlation. Most of you will be doing experimental, either a t-test or correlational with respect to an experimental research design. So Again, I want to reiterate there's two terminologies here. We have research design and then research statistics, right? Statistical analysis. And while some of them overlap, they're different. So in experimental research, what you're trying to do is investigate deliberate controls and manipulates the independent variables to observe the effect and that change on the other independent or the other dependent variables. So let's say we're looking at male versus female on performance. So you're now trying to look at two different variables deliberately and giving them a scenario to measure performance to see a difference between two different groups. So what we want to do is experimental, so we're looking at cause and effect. We find out what the variables of interest are, so that was the exercise we did recently. And what we're trying to see is what's the factor versus a treatment. So we have let's look at it from here, a treatment versus control group. So control group, in most cases, is the group that will not get the factor that you think might cause a difference in performance. When it's gender-based, it's basically two groups. So your treatment group is essentially male versus female, and then you've got performance. But when I talk about treatment versus control group, the example I can give is, let's see if I can go back to my iPad and give you an example. So if I have an example would be let's say I want to take a look at a pilot, a bunch of different pilots, 100 pilots, right? And the control group, we're trying to look at the difference between the control group and the treatment group. And this, I'm giving them basically two scenarios, right? And then I'm going to give them a scenario where the control group, one group of pilots, all similar pilots, I'm trying to make them all similar pilots, similar hours, similar gender, similar background, things like that. The control group would be, let's say, they have a scenario and they're trying to do a cross country from Merrill to Fairbanks, for example. And what I'm trying to examine is the effect of, let's say the effect of the decision to go or a risk score they will give the flight if they were given an airplane with high automation versus low automation, right? So the automation is the factor I'm interested in, right? Automation equals the factor I'm trying to experiment to see and examine if there's a effect of automation on flight. The control group would get the airplane that's not automated, so just basic six-pack or even a G5 avionics, G1000 avionics, but nothing automated, very straightforward. Nothing, in fact, I would just say it's just a basic six-pack Cessna 172, right? And let's say they get this score right here, a risk score, let's say out of let me change that up. Let's say that they have a risk score from 0 to 100, and that risk score is the higher the score, the higher the risk they perceive the flight to be. And the control group gets a pretty high score for this particular example. The treatment group would get the same scenarios, same set of pilots, same experiences. They're all, let's say, instrument-rated commercial pilots with 500 hours, all of them. There's 100 of them here, or let's say 1,000. I happen to get 1,000 here and 1,000 in the treatment group. They're all very similar in terms of experience and education and things like that, just for this particular example. The treatment group would be, they give the same scenario, but I say you're going to get a Cessna 172 with full autopilot and full terrain warning, collision warning, icing warning, all these different automated features. And let's say they give a score that's much lower. Now I can examine and say, oh wow, there's a difference between these two groups. Is it statistically significant? I'll have to do some statistics associated with it. But now I've done an experimental research where I've collected two sets of data from two different groups, and I've given one control group and one treatment group, with the treatment group being the group that's going to get the factor that I'm looking at for a difference, and saying, okay, there's a difference in risk score, perception of risk score, and therefore I can infer that there is a difference between automated flight risk versus non-automated flight risk for a given flight scenario. There's some various basics that you need to be aware of. I talked about confounds, so there's variables that might be confounding your results that you're not looking into. So, while I say, let's go back to that automation example, I'm trying to maintain the same groups, the same factors, things like that. There might be another factor that I didn't look into. Let's say I didn't collect the data to see where they got their experience. Let's say the control group, the one who said it's a very high risk, let's say they're all similar pilots in terms of hours and experience, but in terms of hours of experience and commercial and instrument, all that. But let's say all of them are Florida pilots. So now looking at the scenario of going through mountains is a high risk to them, regardless if they got the automated or non-automated flight, or automated or non-automated features in the airplane. But then the control group, the treatment group, who I gave them the 172 with full automation, let's say they were all Alaskan pilots, all Bush Alaskan pilots, but the same number of hours. They might find flying through the mountains not a big deal. So that's a confound. So you've got to be aware of that. What we want to do then is randomize it to remove some biases, some issues associated with confounds or biases with that. And so you want to assign people or your sample to the control versus treatment group randomly. We'll have to talk about how we do that in methodology, but we always want to randomize our sample to the different groups that we're going to assign them to so that it minimizes bias. Some of the things we want to do is replicate, be able to replicate. We also want to have some variance. Basically, we want to be able to measure the same thing over and over again if we were to repeat this experiment over again. We also want to discuss external validity. So while we try to keep internal validity, we talk about this term internal validity of a research design. How do we make sure it's internally valid? We make sure that we use the right research tools, we use the right scale, the scale is valid and reliable, we're actually measuring what we need to measure, we kept things random, we made sure that we choose our sample size properly, and then discuss how representative of this target population is the sample. Can the results be generalized? So if my research study is just looking at Alaskan pilots, when I take a sample of, let's say, 100 pilots from Alaska only, then I can only generalize to Alaskan population, so the Alaskan pilot population. I can't say, well, these results will also apply to pilots who have flown in Florida, pilots who have flown internationally. That's what I mean by external validity. Does your results from the sample you chose fit a generalization? Will it be able to be replicated to a larger sample or the population of a whole that you're decided to examine, right? All right, so some of the tests that we can be used for experimental research design. So we're trying to look at we're comparing means or averages between groups or different variable answers, right? Or the variables. So t-test is what we'll typically do when we're looking at one or two samples. So really, t-test is really when we're looking at male versus female, or commercial versus instrument pilot. We're trying to keep it between two groups, basically. So that example I gave you with the control versus treatment group of automated flight versus non-automated flight on risk score, that'd be a t-test example. And then NOVA, analysis of variance, would be multiple groups. So we're trying to see, well, is there a relationship between male, female, automation, non-automated, hours of experience, licenses, and history of flight experience. So things like that would be an ANOVA, multiple variables that we're looking at. And at this stage of this class, we probably will not be doing an analysis of variance. That's a little bit more complicated and things that you have to do in order to be able to do an ANOVA. There's a couple statistical assumptions that need to be met before an ANOVA can be done. A regression analysis is essentially a prediction analysis. So it's kind of similar to an ANOVA in the sense that what you would do is create a graph based off different variables and be able to predict a score based off that. So let me give you an example. So if I want to be able to, let's say, profile pilots and say, I want to know how performance, like how they're going to do with respect to a flight. And what I'm doing is essentially creating a graph. I collect the data, and let's say I want to be able to predict their score in a test, a flight test, right? And so that's the y. And basically what I'm trying to do, if you remembered from basic math, your curve or line on a graph is associated by this equation, y equals mx plus b. It's how much of x plus some starting point b, right? And what that says is if I can figure out the graph equation of this y equals mx plus b, I can then determine and predict someone's score if I know the x value of this term. That x value would be, let's say, the aggregate of variables such as gender, experience, income, let's say, things like that. I decide that, and I create an equation that will give me the x, and then I solve and see if this aggregate correlates, so to speak. Remember, there's a relationship between correlation and regression. It correlates to this y score. I can then predict from then on. If you tell me, I'm saying, if you can tell me, if you give me someone's gender, experience, and income, I can then predict based off their x score what their y score will be on the score of the test. Regression analysis is pretty awesome because it gives you, it's basically prediction analysis. Are you going to be able to predict a variable, let's say a score on the test, if you're given gender, experience, and income? And that's really where a lot of prediction analysis comes from data analysis. It's really cool. There was a big topic on big data with Facebook and Instagram and all these different social media tools that were collecting people's data, right? They were collecting their profiles, they were collecting what they liked, they were collecting what they looked at for X amount of time. And based off that data, you can really profile someone. You can really predict what they can potentially do, behavior analysis in terms of that. When you have this X score and figure out what that correlates to on a y variable axis. And that's actually where things get kind of interesting. And you can make some pretty good predictions. You can make some dependable prediction. You can't exactly predict things unless your model's very, very good. But basically what you're doing is modeling a prediction based off data sets. And that's where the experiment comes into play. How many subjects do we need for a sample? Well, it depends on your power, what your power that you want to do based off your hypotheses. I think I'll talk about this on another day when we talk about sample size and determining sample size. But the first few steps you want to be able to do is determine what experiment, research, design you're going to do, either experiment, correlation, or ex post facto. And then you're going to decide how much of a sample size you'll need in order to have a good study. So basically what you're trying to do is define your power, and your power is basically how strong your design is going to be. If I were to simplify that, how good of a design did you make, right? And your power is really defined by the power to have a correct decision, 1 minus beta, and that's really limiting your type 2 error. Okay, I'll have to talk about errors in another class, but basically what we're going to do is use something called G-Power to calculate what the sample size is going to be. And this is what it looks like. This is a software tool, G-Power, that will say, okay, if I'm doing a t-test, that's based off a generic t-test, let's say, and I want to do a one-tailed t-test and the DF of 1, don't worry about that, and I want to calculate how much of a sample size do I need, right? And so that's going to tell me, okay, here's what my critical t needs to be with respect to a power of 1 minus beta of probability error. So to get a strong research analysis. If I did a point by serial model, which is what mostly, nope, we're not going to do that. We're actually going to do means, difference between two independent means, so two groups, right? So we're going to look at two groups, male versus female, on performance. That's what we're going to look at with a t-test. And we're going to leave everything your typical default values, and I calculate it. It's going to say my sample group of size 1 needs to be 88. My sample size of group 2 needs to be 88. So I need a total sample size of 176 people to have a strong power, to have a strong research analysis, to have a strong experimental design, to be considered a strong experiment, right? A good experiment. Now, sometimes you might be limited and not be able to get 176 in this particular example. And so we might have to say, well, that's a limitation of our study. We're unable to get 176. So it might not be as strong with respect to power, but at least we can make some basic inferences. Let's say we get 100 people for our sample, 50 and 50. Well, it's close. It's close enough. It can tell us, well, we're not quite at what was limited for strength or defined for strength, but it's close enough where we can at least make some inferences based off the study and make some recommendations for the next time this study's done, is to try and get a bigger sample size. So that's what we mean. How do we decide how much we need for a sample? This is the basic concept, but what we're going to use for this class is G-Power to define what our sample size should be and what we should be aiming for between the two groups if we were to do a t-test. What else this allows us to do is an f-test. That's for correlation or ANCOVAs. You can kind of see this kind of gives us a nice set of test family tests if you were doing true statistics with respect to statistical analysis. So z-test would be for correlation. So let's say I want to know how much do I need for a correlation. I need a total sample size of 128 in order to get a good correlational value. There's a term called quasi-experimental research. We're most likely going to define our research as quasi-experimental because you have control of when and the whom of the measurement, but lack control of when and to whom of the exposure. So what does that mean? I'm unable to really control you might find it hard to really control randomization between the two groups because of your sample size or limitations based off who you can give the surveys to, for example. So that's when it really falls under quasi rather than true. And so we're not going to go into that much detail as to quasi versus true right now. We just want to define whether we're going to do an experimental, correlational, or ex post facto. So in terms of useful terms, correlation, we're looking at the strength and direction of linear relationship between two random variables. Ex post facto is historic data, and we're just kind of analyzing the historical data using statistical analysis. Quasi experimental in that sense, meaning we're semi doing it as true as we can, but we're unable to really control the randomization effects, which would give it a true statement or true experimental status, but limitations to what we can do this semester. It'll most likely be a quasi-experiment, and I'll help you individually with respect to determining that. Variable is the measure of a factor that we're trying to do. Okay, So that's basically the start of defining your quantitative research design. What I'd like you to do is once you've decided which one you're going to do, I want you to look at these three files, and I will help with that as well, and kind of determine which one you're going to do and how it's going to be done. I'll be making some videos next week over these three, but I wanted to at least get this out for you to review. And then, like I said, again, our overall goal is to make a proposal document. So you've done some of the work already with the proposal, but what I'm trying to do is have you come up with a full proposal document that will look like this. This is a previous proposal that I've worked with a student on, just to give you an idea. So the background is based off your literature review. You're trying to link your background, your literature review, to the topic, why you're doing it. So your literature review, based off what you've done, should outline what the literature review did, what their approach was, what they modeled, what the results were, and how it's linked to your study. So you can see here how this was done for this particular example, what was used, what the participants were. So like here, the participants in this research was XYZ. The actual scenario was this was the actual scenario that was given in that literature review study. So it's kind of showing you what you've done in terms of literature review, what the results from that previous research is, and how that implies to, or how you are going to utilize that for your own research study. And then you want to summarize the research literature review into your own study, right? And then usually the last sentence is, therefore research is needed to show XYZ and why you're doing your research study. Then we go into the problem and purpose statement of your study, right? So you want to have a narrative hook, you want to explain why you're doing the study, what your purpose of the study is, your operational definitions of your study, your variables. You see where we did all this work in the past, but now it's more, expanded out. You want to look at your research questions and hypotheses. It's a short paragraph, but now you've done that and you're writing it out in a document form. And now we're working on methodology. We're looking at participants. Who are your participants going to be? So defining who your participants are going to be for your study. Your estimated number of participants. And also we'll talk about that in terms of G-Power. So I'll explain, download G-Power and figure out what your minimum student or participant value needs to be. Your procedures and materials is the hard part. This is where you need to figure out what you're going to do with respect to your materials to collect with respect to data analysis, right? So your data collection, when it will be collected, how it's going to be collected, what information you're going to get, and what type of research you're going to do. So you're going to discuss whether you're going to do an experimental design, ex post facto, or correlational research. So that should really be before participants. This is missing the methodology as to research design methodology, and explaining what you're going to do and why you're going to do it. Significance and practical implications. So you're going to explain what you're going to do as to and why you're going to do that, and then the limitations and delimitations. What are you going to limit to your study? Because obviously you can't do everything. So what is limited with respect to your study? Time is usually the biggest issue. All right. So that's what we're working towards, is the example proposal, deciding what your participants are going to be, and your methodology of collecting data. So when we talk about procedures and materials, one of the things the student lacked in terms of the methodology was explaining what methodology is going to be used. So in procedure-wise, you would briefly explain that this study is utilizing an experimental design, or an ex post facto design, or a correlational design, right? And the statistical analysis that will be used will be a t-test, or correlational statistical analysis. And then explain how you're going to gather the data. Okay? Here you go. He did have it. I'm sorry. This study will be an experimental design as the participants will be randomly assigned onto 1 to 2 groups, the random assignments, and so on and so forth. So it is actually explained here, I apologize. So this hopefully will help you gather and get an idea of what you need to be doing for your proposal. And you have 3 weeks to work on this. You have week 6, week 7, week 8, and week 9 is when it's due. And we'll be doing the IRB, the Institutional Research Board, for ethics in terms of the ethics research element of things on week 9.